Welcome back. So we covered gradient descent last time, and it seemed to work pretty well. But there's an improvement to gradient descent called conjugate gradient descent that can be used to perform even better than what we talked about before. And we'll start by making an unrealistic assumption. This is actually common in signal processing. You assume you know a bunch of things, you prove the result, and then you go back and figure out how you're going to estimate those things that you actually don't know, or make do without them. Okay, so let's suppose for a moment that we know n step directions that we're going to take. Okay, and we'll call these would be vectors, d0 through dn minus 1. And let's further require that each step is orthogonal to all the others. Okay, doesn't mean they're not, in this case, they're not necessarily normalized, because we may take steps of different lengths. But it does mean that dj transpose di is equal to 0 for I not equal to j. Okay. Well, this is a lot of assumptions, but you could see maybe some of the benefit of doing this, because what goes on with a typical gradient descent is that we bounce around on our way to the solution. In other words, like a drunken man trying to reach a goal, we may sometimes move forward, we may sometimes move to one side or the other, and we keep hitting directions that we've already stepped in. If we could just make sure that every direction that we go is orthogonal to the others, we're not going to be undoing steps that we've previously taken. Well, right now this is all pretty fantastical, but it turns out that this is a good place to start thinking about a solution, because if we do this, if we look at the problem this way, I should say, then we could say that dk over norm of dk forms an orthobasis for Rn. Okay. So let's go back to our gradient descent problem. Back to gradient descent, we had to start at a particular point, and we called that x0. Well, if x hat is our optimal, then our initial error we define as E0 is equal to x0 minus x hat, which is our solution. Since we have formed this kind of arbitrary basis based on our step directions, we can go ahead and expand our error in terms of that. Like so. So, just a simple orthobasis expansion into this somewhat arbitrary space. Okay, now let's follow through and see what happens when we start doing our gradient descent and express it in terms of what we have here. So here we'll have EK, so at the kth step, define that to be xk minus x hat, but that's equal to xk plus alpha k minus 1, and then dk is the direction that we were going, minus x hat, which is just equal to the error times k minus 1 plus alpha k minus 1 times that previous direction. And we can keep doing that. It's equal to e k minus 2 plus alpha k minus 1 d k minus 1 plus alpha k minus 2 d k minus 2, and so on, until we finally get down to the expression E0 plus L equals 0, k minus 1, alpha L, dl. Okay, so now if we were to somehow magically choose our step sizes, our alpha k's, just right, we could one by one peel off each of these contributions to the error, and essentially we just need to pick alpha k is equal to negative ck over dk is equal to negative dkt E0 over dk squared. So if we do this, remember that we had up above this expression for E in terms of each of these. And so now we're saying we take E0 and we sum up all of these alphas along the way. And in each one, it's perfectly designed to cancel out the corresponding term in E0. So as we increase k, we just one by one peel off each of these terms from E0 until pretty much we're down to our minimum error, which should be 0. So if we do this, then we have dk is equal to the sum from L equals k, so it's grabbing all the remaining terms that we haven't yet peeled off, dk over dk, and the norm of ek squared will be equal to, likewise, that same sum, but now just times ck magnitude. So as k increases, eventually we get down to En equals 0. Okay, but we made a lot of assumptions along the way. You can see that some of them might be okay. But one of the big assumptions is we don't know the initial error. So if we knew the initial error exactly, we would be there. Of course, if we knew the initial error, then since the error is defined as the difference between where we are and the correct solution, we would necessarily know the correct solution. So pretty much we're never going to get the initial error. So we have to see if we can find some other way to work. Well, the key to conjugate gradients is the recognition that orthogonality can be defined using any inner product. So let's define an inner product based on things that we do know. So for conjugate gradients, we use the inner product dj with di is equal to dj transpose h di. Okay, so since h is symmetric and positive definite, this is a valid norm, or a valid inner product. They didn't quite fit it all on one page. Okay, so instead what we do is we say that E0 is equal to a sum of H orthogonal vectors. So D0 through Dn minus 1 are they're orthogonal with respect to H, this new inner product, where, of course, since it's based on the inner product, we have di H is equal to di transpose H di. And of course, CL is going to be now the same thing, but just defined differently. This will be E naught dl for our new inner product, dl H, which can be just expressed as d L T H E naught over dl H. Okay, so remember we started with this whole idea saying we have n orthogonal directions that we are going to step when we do our gradient descent. And when we're talking about one-dimensional systems, obviously there's only one direction we can go, but the more dimensions you have, the more directions that you could possibly step as you're working your way down to the minimum. It turns out that we couldn't actually implement this because we don't know E naught. However, we can, in fact, solve problems with conjugate gradient descents anyway. The PDF notes talk more about it. But I'm going to summarize the results right here and discuss them a little bit, and then if you want to see the proof, you can go back to our notes. So for conjugate gradients, we follow this procedure. We initialize with just x naught as before equals some guess. If you have a good idea of what your solution might be, maybe you could start there. Maybe you had a solution to a similar problem from last time. Things have changed a little bit, maybe. Perhaps you're using a communication system and you happen to know what the guess was before, but now we've had a slight change in our system response or transfer function. And so we need to come up with solve the problem again, but at least starting with our previous guess isn't a bad place. If you don't have that, starting with a guess of 0 is a tried and true method of proceeding. And so here's our initialization. Then we do a loop. Okay, equals 0 to n minus 1. We first define alpha k is is equal to R K transpose RK divided by dk transpose H dk. So these are all quantities that we have, and we compute that. Next, we update our x k plus 1 is going to be x of k plus alpha k dk. And now that we have our new x, we can find our new residual. Rk plus 1 is equal to Rk minus alpha H dk. And we have that beta k plus 1 is equal to, we haven't introduced the beta yet. Talk about it also. And finally, we update our new direction as R k plus 1 plus beta k plus 1 dk. Then we end. Okay, a few things to point out here. This is performed n times. And in the PDF notes that go with the class, we can actually prove that this does converge in n steps. Well, this seems fantastic. N steps is much better than we would expect with regular gradient descents, and it doesn't look too bad. However, we've got this application of H, and so each step, each iteration through this loop, let's put it that way, each iteration has O n squared complexity. Thus total complexity is O n cubed, and O n squared n times gives you O n cubed. That's the same as solving it directly. So this seemed like such a wonderful, great thing. Why are we even discussing this if it doesn't help much? Well, it does actually help. Although it may take as many steps as other solvers. Often, let's see, I like that. However, H has structure that is taken advantage of, utilized. To reduce implementation of doing our dk transpose h dk. So that helps a little bit. But the real help is that the error is often sufficiently small for just a few steps. So if we don't need an exact answer, we can get an approximate answer that's still potentially quite good, that uses far fewer iterations than you would see otherwise. Since we've boxed this beautiful little summary here of our conjugate gradient descent algorithm, it's quite easy to implement. And I think I'll step back here and introduce a similar algorithm so we can compare this to our regular steepest descent algorithm. With steepest descent, the algorithm starts out as before. We initialize. And here we say x naught is equal to some guess. The better that initial guess is, the better off we're likely to be, but it's not critical. And we likewise say that r naught is equal to b minus hx, as before, hx naught. Now we're not doing a for loop, we're doing a while loop. So we're going to initialize our loop counter to k equals 0, and we do while the residual rk is greater than or equal to some delta. We calculate our alpha, rk transpose rk over rk transpose h rk, and we have x k plus 1 just equal to xk plus alpha rk. And then we have r k plus 1 is equal to b minus h x k plus 1. Increment our index, and that's it. So one thing to note, once again, the most expensive part of all of this is the application of our H matrix. And so we can simplify the computation a little bit by noting that rk plus 1 is equal to b minus h xk plus 1, which is equal to b minus h xk plus alpha k rk, which is just r k minus alpha h rk. So there are two places when we need to apply our H matrix. One of them is here to H times RK, and the other is right here. Well, we've just expressed this quantity in terms of H RK plus 1, and so we can modify this whole procedure just a bit to make it a little bit more efficient by saying Q is equal to H RK, alpha K is equal to RK transpose times RK over now RK transpose Q. XK plus 1 is just as before, xk plus alpha k rk, and rk plus 1 is just equal to rk minus alpha q, and then we increase our loop variable. So this is a little bit more efficient and an alternative way of implementing our gradient descent. So flipping back to the previous slide, in the previous slide you can see we apply h times dk twice, so we could do the same type of a thing. We could pre-compute that, and that will help. We also notice we have just a little bit more complexity, but not much, with gradient descent or conjugate descent. And so here we have our steepest descent summarized, and there we have our gradient descent summarized. So how much better does the conjugate descent work than the gradient descent? Well, we can place bounds on how fast things are going to converge to a certain error point. And this is discussed just briefly, but not proven, in the PDF notes. It's also something that's discussed more in the adaptive filtering class. But to give you an idea, it depends a lot on the maximum eigenvalue to minimum eigenvalue ratio of H, and it works much better when those two, the max and the min eigenvalue, are very close to each other. But if you had, say, a ratio of 100, which would be our condition number, then the conjugate gradient descent, in order to get down to a 6-digit precision, or an error of 10 to the minus 6th, the conjugate gradient descent would be about 10 times as fast, taking about 70 as opposed to 690 for just standard steepest descent. So the conjugate gradient descent is a big boon, and there are some homework assignments that deal with and compare both of those.